Hello, Chemistry 11 Honors. This is Mr. Chan. And before I go on to today's video, what I wanted to do was talk about last day's video. And I realized I made a little technical boo-boo. And this one should not be plus 20. It should be negative 20 kilojoules. Sorry, my bad in that aspect. Okay, so just a little mathematical error. Now, what I wanted to do today was one final bit when we talk about delta H, and that is something called lattice energy or lattice enthalpy. So what it is, lattice energy or lattice enthalpy is the energy that is released when gaseous ions form an ionic solid. The key word is that it is energy that is released. So it's an exothermic reaction. So in this case, an example here would be like sodium ion gas plus chlorine ion gas would form sodium chloride. And what you would get is you would get a negative 788 kilojoules per mole. Now, a couple of things about this lattice energy. The lattice energies of ionic compounds are generally large negative values, indicating that the ions are strongly attracted to one another in the solids and are more stable. It is this strong attraction that causes most ionic materials to be hard, brittle materials with high melting points. So in this case, because the lattice energy is so exothermic, that means that if you were to take a look at this, these ions are what we call unstable, while this solid, since it's exothermic, is very stable. And because they're very stable, they're considered very strongly bonded. Now, one thing about this lattice energy, the magnitude of the lattice energy of a solid depends on the charges of the ions and their sizes, as well as their arrangement in the solid. Now, if you take a look on page 365, what you will see is in page 365, you talk about lattice energy, okay? Now, if you scroll down, you take a look on page 366, what they do is they compare the lattice energy of magnesium oxide versus sodium fluoride. Now, look at the difference in the lattice energy. For magnesium oxide, the lattice energy, notice, is extremely large. It's very exothermic compared to sodium fluoride, which is not so much. Now, the reason why you have a difference is because, take a look, for sodium fluoride, you have one positive and one negative ion. While if you take a look at magnesium oxide, you have a Mg +2 and an oxygen -2. So what happens is the charge, because it's a +2 and a -2 charge, what happens is there's more energy given off when they are combined together. Now, this idea comes from the idea of this lattice energy from the formula of Coulomb's law. Okay, so you can take a look at the background and they talk about what does the K mean? What does the Q1, Q2, and R mean? And for you to give you some background materials to that. All right. Now, so let me see here. Now, lattice energy cannot be determined directly by experiment, but it can be calculated by envisioning the formation of an ionic compound as occurring in a series of steps. When one takes into consideration all the steps for the formation of an ionic compound, it's called the Born-Haber cycle. Now, so notice what you have is a series of steps. What you have is you have these symbols on the left, delta H0 formation, H1, H2, H3, H4, H5. It's a combination of these steps that you can determine the lattice enthalpy. Now, this relates back to where we had Hess's law, where we had a series of steps. When we combine them together, it gives us the energy for the overall reaction. Okay, now, some of you might say, well, what is this H1, H2, H3, H4, and so on? Well, what it is it's a series of steps. So H1 and H2 is called the enthalpy of atomization or enthalpy of sublimation. And this is the enthalpy change required to produce 1 mole of gas atoms of an element from the element in the standard state. So in this case, for H1, you are going from sodium solid, which is the standard state, to sodium gas, while H2, you're going from chlorine gas molecules in a standard state to chlorine gas. So if I were to do that here, I would put a little G. Now, ionization energy, H3, is the enthalpy change for 1 mole of gas to lose an electron. 1 mole of gas element or cation to lose electrons to form a mole of positively charged gas ion. So if you look back at the little scale there, you had sodium gas going to sodium gas ion. Enthalpy change, H4, electron affinity, the enthalpy change when 1 mole of gas or anions gains an electron. So 1 mole of gas or ions gains electrons to form a mole of negatively charged ion. So in this case, if you look back at H4, you are chlorine gas going to chlorine gas -1. That is what we call electron affinity. And lattice energy is the energy change when the ions form a solid. So notice you have your positive ion and your negative ion forming your solid. Now, using this Born-Haber cycle and Hess's law, one can experimentally determine the lattice energy for a particular solid by using this formula. Okay, now, one thing that you could take a look at is, notice on the left-hand side, I have H1, H2, H3, and negative HF. Now, you could think of it like this. If I were to break this down in half, we have all the energy going up should equal all the energy going down. Now, why is it negative HF? Because look at what heat of formation is. You compare that to H1, H2, and H3. Notice H1, H2, and H3 are all going up. HF is going down. So we need to flip the arrow. And how do we do that? We put a negative sign to it. So all the ones here, HF, H1, H2, H3, should equal H4 and H5, but opposite. Okay? Now, this goes back to, remember, Q reaction is equal to negative Q surroundings. All right? So, say for a typical example here, it says calculate the lattice enthalpy for LIF given the following information. So what we do is, in this case, H sublimation, this would be H1. Okay? Now, first ionization energy would be here, would be H3. These two would be H2. Electron affinity would be H4. And the heat of formation would be HF. So what we do is, again, remember, we take H1, H2, H3 minus HF, and that would equal to negative delta H4 and H5. So here we have 161 plus H2, which would be 77, plus H3 would be 520, minus negative 617 would equal to negative H4, which would be negative 328 plus delta H5. Delta H5 is the what is it? Lattice energy. So in this case, if we added up everything to the left, 161 and 77 and 520, 617. So I would be 1375 is equal to positive 328 minus delta H5. If we isolate, delta H5 would be equal to minus 328. So this would be negative 1047 kilojoules. So this is just basically an elaboration on delta H and Hess's law, but specifically talking about formation of a solid from its component ions. Okay. And it does make sense. Remember, it should be exothermic. So delta H5 is exothermic. So that should be correct. Now, if you take a look on page 366, 367, I believe, and they actually do the exact same example. Okay. Now, oh, yeah, there you go. My heat of formation here, or sorry, lattice enthalpy is negative 1047 right here. Okay, so they did the calculation right here on page 364. All right, folks. Now, in your textbook, they do it a different way. Okay, whichever way works for you, that's perfectly fine. So if you take a look in your Zoom-Doll text, they do talk about a different way of approaching it. I teach it a different way, but both answers are correct. Now, the one thing I would like you to be aware of is notice for C, they are the same values actually, because here you have F2 breaking apart to 2F would be 154 kilojoules. But since I only want one F, so that's half F2 gives you F. This is how you get 77. Okay, so both of these are basically the same. All right, folks, thank you very much. Have a good day. Bye-bye.